as we start 11-2, we're going to look first at vocabulary, making sure we've clearly defined our terms we're going to be using as we progress through this material and start getting into calculating the probability of specific events. First, we should probably lock down what we mean by probability. Probability is the measure of how likely an event is to occur. So it's a calculation. It's a value we assign to say this event is likely, this event is unlikely. Now, a word about probability. Probability will always range between 0 and 1. Now, if the probability of event A, that is something, and A can be anything. It can be rolling a 1 on a 6-sided die. It can be drawing the ace of spades out of a standard deck of cards. It could be getting a date with the girl next to you in class. Anything that can happen can be categorized as an event. The probability of that event ranges then between the values of 0 and 1. It's always going to be a decimal, or a fraction, or a percentage, and you should be comfortable using all three of those. If an event is down here at 0, that means it's not going to happen. It's impossible if the probability is 0. We get up to 1, it's now guaranteed to happen. It will always happen. So if the probability of something, an event, is 1, it happens in every instance. 0, it never happens. And then most of the probabilities we're interested in are somewhere in the middle. Some 40%, 30%, 98%, 1%. Those are the ones we're going to focus on the most because always never isn't very interesting because either always happens or it never happens. Now when we talk about sample space, a sample space refers to a listing of all the outcomes. So if I wanted to talk about the sample space for perhaps flipping a coin, I have heads and I have tails. And that set represents all the possible outcomes. I sometimes will also abbreviate that as simply H and T. H for heads, T for tails. So again, the sample space is just a list of all the possible outcomes. I want to talk about rolling a standard 6-sided die. The list of the numbers 1 through 6 represents that sample space. It represents all the possible outcomes in that area. Probability and sample space are going to be two words we're going to use a lot in this section, so we really want to be sure we have that vocab locked in. Next, we want to start looking at actually calculating that probability. For this, we're going to need to think about two sample sets. We're going to need to think about how many different ways an event can occur and how many ways we want to have happen to represent a successful outcome for event A. So let's take a look at this example here. It says 6 people order coffee, and of them 2 are going to order mochas. If one person grabs a random cup off the counter and says, "Oh, I got mine, I'm out of here," what is the probability that they're going to pick the mocha? Now, notation. When I write the letter P, and in parentheses list something, a name, describe a situation, or simply put a letter, I'm talking about the probability of that event occurring. This is mathematical shorthand that we're going to be using throughout the chapter. So when I do this, I'm asking now, what is the probability that a mocha is selected? All probabilities boil down to one basic fraction. When we talk about the probability of a given event, at its most simple, we're looking for the number of favorable outcomes out of all of the total outcomes. So in this case, I need to figure out how many are what I want to have happen versus how many ways can it happen, and then that fraction will give me the probability of the event I'm looking for. There are 2 mochas out of a total of 6 cups. So the probability is 2 out of 6. As a rule of thumb, you always want to reduce your fractions down into decimals and turn them into percentages because you never know what means people want to communicate it. So for practice here in class, you want to focus on knowing how to use all 3 sets. So I can take my 2/6 and reduce that to the fraction of 1/3, which is the same as 0.33333 repeating. and as can be expressed as 33%. Now, for our purposes in rounding, I'm safe to leave this at 2 significant digits, round it to the nearest percent. Only worry about going past the closest percent if we're dealing with incredibly small probabilities. In those cases, yes, you would want to take it a little bit further, but for what we're going to do, that's plenty. Let's take a look at another problem now. Our next example is going to involve a problem from the dice game Craps. You'll see it in a lot of casinos. It's a very popular game because it's very social. In this game, the point is 6, which means the goal of the shooter, or the person rolling the dice, is to roll a 6 before he rolls a 7 or an 11. Now, the question in front of us is, what is the probability then that if the player rolls 2 dice, adds them together, that he's going to get a total of 6? To answer this question, we need to first find out how many different ways can you roll a 6 versus how many total outcomes are there for 2 dice, your standard 6-sided dice in this particular case. And if it's not that, I'll make sure to tell you. So let's actually start to map this out and take a look at it. For example, on my first die I can roll a 1, and on the second die I can roll a 1 as well, for a total of 2. Maybe I roll a 1 and a 2. That would be a total of 3. And then maybe a 1 and a 3 for a total of 4, 1 and 4 for a total of 5, 1 and 5 for a total of 6, 1 and 6 for a total of 7. And then I should go on to look at the other possibilities. So 2 and 1, 2 and 2, 11, and 6 is 12. There. All the outcomes are up here finally. Now, when I look through this sample set, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, that represents all the outcomes. Now there are 6 this way and 6 that way, which totals out to be 36 combinations. Now if I wanted to use the work from section 1 with combinations and permutations, that may have sped this along just a little bit. But we've got them all here in front of us now. And that's important because it lets us look to see how many different ways I can generate a 6 on these 2 dice. I can do 1 and 5, 2 and 4, 3 and 3, 4 and 2, 5 and 1. Those all represent ways to get 6 as my total, out of 36 total possible combinations. So the probability then would be 1, 2, 3, 4, 5 out of 36. Unfortunately, that's not exactly a fraction I can reduce. No number divides evenly into both 5 and 36. So we can now go ahead and turn it into a decimal. So we'll break out the calculator. 5 divided by 36 puts me at 0.14. It's actually 0.138 repeating, but we're going to round it to the nearest hundredth and get an answer of 14%. Not exactly great odds when you think about it. That's just between 10 and 20% of the time. Now remember, if you follow the game at all, the game ends if you roll a 7 or, I believe, an 11. But 7, 1, 2, 3, 4, 5, 6. 6 out of 36 is greater than 5 out of 36. You're more likely to fail than you are to win, which is why casinos do like to bring people into this game. They're more likely to win than they are to lose. Again, to do this probability, it really does boil down to simply asking myself, how many ways can I generate a value? In this case, the 6. How many total ways are there here? 36.